A linked list is a chain of nodes.
Each one holds a value and a pointer to the next one. You start at the head and follow the pointers, and eventually one of them points at nothing, and you stop. That is the end of the list, unless it does not. If some node points back at an earlier node, there is no end. You follow the pointers and you go round and round and round. That is a cycle, and a program that walks this list never finishes. So, how do you find out whether a list has one? The obvious answer is to remember every node you have visited. Keep them in a set, and if you ever arrive somewhere you have already been, there's a cycle. That works, but it costs memory proportional to the length of the list, and the whole reason this problem is famous is that you can do in constant memory. Here is the idea that gets you there. 2 pointers from the same start. The slow one moves 1 node per turn. The fast one moves 2. If the list ends, fast falls off the end and you're done. There is no cycle. But if there is a cycle, both pointers end up going round it forever, and the fast one gains on the slow one 1 node per turn until it lands on it.
Same node, no memory used. That is cycle detection.
And that was the easy half. The hard half is the question people actually get asked. Not is there a cycle, but where does it start? The standard answer is a piece of magic. You put 1 pointer back at the head, you move both 1 step at a time, and they meet exactly at the first node of the cycle. Almost everyone memorizes that. Very few people can say why it works.
And it starts with a question. When a fast pointer finally catches the slow one, where exactly are they standing?
Most people say the start of the cycle. That is wrong in 91% of the lists I tested.
They almost never meet at the start of the cycle.
By the end of this, you will be able to derive the whole thing in 1 line from a single fact. For things, the picture that taught you the wrong answer, where the pointers actually meet, why resetting to the head lands exactly on the entrance, and why the fast pointer moves 2 and not 3, which almost every explanation gets wrong. Here is the diagram you learned this from. A cycle and nothing else. Run the pointers. They meet at the entrance. So the belief is not careless. In this picture, it is simply true. The trouble is that this picture has no tail. So get one. 3 nodes, then a cycle of 4. The cycle starts at node 3. Step 1. Slow is on 1. Fast is on 2. Step 2. Slow on 2, fast on 4. Step 3. Slow on 3, fast on 6. Step 4. Slow on 4. Fast on 4.
They meet on node 4.
The cycle starts at node 3. They met 1 node past it. That is not a fluke of small numbers. 6 nodes of tail and a cycle of 4, and they meet 2 nodes past the entrance. But make the tail 4 instead of 6, and now they do meet at the entrance.
It is the entrance exactly when the cycle length divides the tail length.
A tail of 0 divides by anything. That is your textbook diagram, right? So where do they actually meet? Let us do this properly. 2 names, and they're the only 2 you need. X is how many nodes you walk before you reach the cycle. Y is how many nodes are in the cycle itself. In our list, X is 3 and Y is 4. Now count steps. After T steps, slow has walked T nodes. Fast moves twice as fast, so fast has walked 2 T nodes. Subtract those. Fast is T nodes further along the list than slow. Not 2T, just T. Once they're both going round the cycle, being T nodes further along means being T nodes further around the ring. And a ring of Y nodes wraps every Y steps. So walking T nodes forward lands you back where you started only when T is a multiple of Y. Watch that on our list. Y is 4. At step 3, fast is 3 ahead. 3 is not a multiple of 4, so they are on different nodes. At step 4, fast is 4 ahead. 4 is a multiple of 4, so fast has gone exactly 1 full lap and landed back on slow. And that is exactly the step where we watch them meet.
So the meeting time is always a multiple of the cycle length.
That one sentence is the whole algorithm. Hold on to it. The earliest one that is big enough for slow to be inside the cycle is Y, rounded up to clear X. In our list, that is 4. And here's the part that matters. Because they meet after a whole number of laps, the node they land on is exactly X steps short of the entrance. 3 steps short in our list. Count it. From node 4, 3 steps forward is node 3, the entrance, which is the whole reason the reset works. Put one pointer back at the head. Leave the other at the meeting node. Move both one step at a time. The head pointer needs X steps to reach the entrance. That is what X means. And we just showed the meeting node is also X steps short of the entrance. 2 pointers, the same distance from the same node, moving at the same speed.
They arrived together because they were always going to.
Not a trick, not a coincidence, just a fact we proved read backwards. Which brings us to the question nobody answers properly. Why 2? Every explanation says 2 guarantees the fast pointer catches the slow one. That is true. It is also not the reason. Try 3. Slow walks T, fast walks 3T, so fast is 2T ahead. They still always meet. I checked every shape up to 60 by 60. But now they meet when 2T is a multiple of Y.
Which does not make T a multiple of Y.
Here is what that costs. No tail, a cycle of 4, fast-moving 3. They meet at node 2, halfway around. Reset one pointer to the head, step both by 1, and they never meet. Not the wrong answer. An infinite loop.
2 is not about catching. 2 is what makes the meeting time a multiple of the cycle length.
3 edge cases quickly. A self-loop. Cycle length 1, so it divides everything, and they meet at the entrance every time. No cycle at all. Fast runs off the end, and you return null. That is the only null check you need. A tail of 0. They meet at the head. Phase 2 takes 0 steps, and you return the head. Here it is in 11 lines. Phase 1 finds a meeting node. Phase 2 walks 1 pointer from the head and 1 from the meeting node. The line that matters is the reset, and now you know why it is legal. Let's run it. Same list. Tail of 3, cycle of 4. Both pointers start at node 0. Fast is not null, and fast next is not null. So we keep going. Slow moves to 1. Fast moves to 2. They're different, so round again. Slow moves to 2. Fast moves to 4. Different again. Slow moves to 3. Fast moves to 6. Still different. Slow moves to 4. Fast goes 6, 3, 4. Both on node 4. The loop ends. Now phase 2. Slow goes back to node 0. Fast stays on node 4. Step. Slow is on 1. Fast is on 5. Step. Slow is on 2. Fast is on 6. Step. Slow is on 3. Fast goes 6 to 3.
Both on node 3. That is the entrance, and we return it.
3 steps in phase 2, which is exactly X, just as promised. For things to walk away with. 1. The pointers meet X steps short of the entrance, not at it. 2. They meet at the entrance only when Y divides X, and a tail of 0 is why the textbook picture fooled you. 3. The meeting time is always a multiple of Y. Everything else follows from that. 4. The fast pointer moves 2 because that is what makes the meeting time a multiple of Y. 3 still catches up and still breaks phase 2. So, back to the question I opened with. When the fast pointer finally catches the slow one, where are they standing?
X steps short of the start of the cycle.
Not at it, short of it, by exactly the length of the tail. Which is why walking a pointer from the head, X steps arrives at the same moment. The reset is not a trick you have to remember. It is that one sentence read backwards. And the picture we started with. A cycle and nothing else. In that picture, the tail is 0, so X is 0, so they really do meet at the start. It was never wrong. It was just the one shape where the answer looks simple.
It was just missing a tail.
Next time you see a fast and a slow pointer, do not ask whether they meet. Ask what the gap between them is doing. That is where every one of these proofs lives.